So, hello everybody. Hello with a traditional short delay. So I choose a short version of introduction. Welcome at the opportunity of the next episode of our lovely Prague seminar for mathematical physics. And it's my great pleasure. I can introduce Fridrich Valach, who kindly came to us from the University of Hertfordshire, and he's not alone. He's with his nice-looking topic. It's on a generalized Ricci flow for Courant algebroids. So this is another catchy topic in a row. And yeah, last thing I would like to say is that Fritzo holds a postdoctoral position at this university, but on the other hand, he's a kind of regular speaker here, so no other updates on this account. So thanks again for coming.
Thank you.
For us.
Thanks to everyone for coming. So thanks for the invitation. So I would like to tell you something about our newest work, which is on the archive a month ago. And it's about generalized Ricci flow on algebroids. So it's a joint work in progress. Sorry, not in progress. It's a joint work with Jeffrey Streets and Charlie Stephen Constable. And so the idea is the following one. So let me start with some idea. So in ordinary geometry, you start, okay, so consider a situation where you have a manifold, and then you put a random metric on it. So you put some Riemann and metric on it. Now, if you have a metric, you can calculate various types of Ricci and Riemann and whatever curvature tensors. And one of them, namely the Ricci tensor, has the same index structure as the metric. So we can use it, it's a symmetric tensor, so you can use it to deform the metric a little bit. You get a new metric, then you calculate the Ricci tensor and you deform it again and again, and this way you get some sort of flow, or you get an evolution on the Ricci tensor. So if you imagine that you put some extra auxiliary parameter, some sort of time, then you can write down the nice looking equation that the evolution of G, which depends on some time parameter, is given by -2 Ricci. So 2 is just conventional. So the point of this equation is that it's a very nice equation. Well, it's horribly nonlinear, but if you squint your eyes, you know, it sort of looks like a heat equation, in some sense, and it has some very nice smoothing properties. So, for instance, if you take your favorite surface, two-dimensional surface, and you put a random metric on it, and you let it evolve under this thing, and you normalize it at this total volume is 1, then you will see that it will evolve to a metric of constant scalar curvature. So it so the flow has this kind of nice smoothing property. You start with something random, and it makes, as you flow along it, it's smoothened out. So unfortunately, if you go to higher dimensions, then there are singularities that typically develop, and stuff may blow up because the equation, after all, is very nonlinear. But still, this is the idea that Hamilton suggested in order to tackle the famous Thurston's geometrization conjecture, and in particular the Poincare conjecture. And this study of the singularities and all that, this wasn't finished by Perelman in his famous proof, for which he got these various prizes, or was offered. Right, so this is a very famous thing. It's kind of very well-known construction, very well studied. Now, what I would like to talk about today is kind of the analog of that in generalized geometry. And it turns out also that it has some very nice applications. It's sort of parallel to the Perelman, or like the Poincare conjecture. So for us, the analog of a manifold will be a Courant algebroid, which I will formally define in a second. Courant algebroid. And the analog of metric is played by something that I will call a generalized metric. And now you can try to write down the same equation. And it will not work because there is no such thing as Ricci tensor, which depends on a generalized metric. But if you fix some extra data, then you can make it work. And the extra data for today, it can be done more generally, but today I will take this extra data to be a house and city. So if you specify a half density, then you can define a Ricci tensor. And then because you have a new datum here, you have to write an evolution equation for that, and the natural one will be given by scalar curvature. Again, depending on G and sigma. So there is some sort of analogous flow equation. It looks pretty much like this one, but slightly different because there is some extra datum. But still, the claim is that this equation is very interesting. First of all, it's related to physics. So I mean, in string theory, this is the normalization group law for the string sigma model. And mathematically, this has been shown by Street and Tian to be related to the classification of complex surfaces. So there is a proposal that you can use this in a similar way to how Perelman and Hamilton used the classical case. You can use this to start to get some very deep and potentially very big results. But in order to do that, you really need to develop the theory of singularities and all of that, and we are very, very far from that. So today I will present some very basic results such as the finite short time existence and uniqueness of the solution and things like this. So it is like the first step towards that. Okay, so that's all I wanted to say at this stage. And now I will try to formally define these things. Okay, so let's start with, how do they call it? Courant algebroids. Okay. I suppose most of you have seen those on numerous occasions, but I will still go quickly through the definition. It's very easy to set up the conventions. So I will find a non-representation. So Courant algebroid is the following data: the vector bundle or some manifold M. There is a bracket operation on the space of sections. Then there is a vector bundle map or rho that goes from E to Tm, the tangent bundle. And finally, there is a fiber-wise pairing. So this is every fiber. And there is some condition this is supposed to satisfy. So let me be brief. Let's say Jacobi. And the other one, let me write explicitly. So if I take two sections, U and V, and I multiply the second one by a function, so this will be something similar to how the Lie bracket of vector field works. So I get a term like this, but then I get another and the extra term where I act on the function, and for that I use the anchor map. So I transform the section U into a vector field using this map and act on it on F. Now from this you can, from this property, so zooming in for a moment on this property, this thing tells me that if I have a section U, then I can act with it on other sections by taking the bracket. This thing I act on other sections. Roughly act on other sections. Or I can use the anchor map to turn this into a vector field, and then I can act on functions on the base. And I can combine these two operations in the usual way that people do in geometry, and I can define a Lie derivative. So I can define curly L of U to simply using the Leibniz property. So using Leibniz, using derivative property, I can extend this to act on any tensor in E. So any tensor power, okay, and also anything in the dual, and it will be consistent. So I can define a derivative, a generalized derivative. Okay, so doing that, I can write the next properties. So far we have Jacobi and this one. Now the other properties that I want is that Lie derivative of the pairing, seen as a tensor, 0. And the last property is that the symmetry part of the bracket is unfortunately not 0, but it's controlled by the inner product. So I take the inner product of these two sections, get a function, and then I apply this operator curly D, which is some nice operator that goes from functions to sections. And the way this goes is that you take function, take a differential to get one form or section of E star, of T star, and then I apply the transpose of this map to go from T star to E star. I apply rho transpose rho star, and this is the section of E star, but I can identify E star with E using the metric, using comparing. This is what I will assume throughout. This is how it's going to be, and that's the end of the definition. So if you see it for the first time, then it probably doesn't tell you, it's not obvious that this is a meaningful thing to do, but it is. Okay, so right. Now this is the end of the definition. Now it's not difficult to show the following property that in fact we always have a chain complex. I apologize if this is boring for some of you. I assume that most of you have seen this. Also for me, several times. Okay, so there is the chain complex, and definition you say that the Courant algebroid is exact. If this is an exact sequence. And it's also transitive if it's exact here. So if rho is surjective. Okay, and the basic structure of theorems here, just to give you some examples. So theorem due to Fridrich is that it's a complex classification of exact Courant algebroids. So maybe I forgot to say everything is smooth, but I suppose you have seen it. So every exact Courant algebroid is of the form E equals Tm plus E star m, with rho simply being the projection, so take X vector field on one form, then X. Pairing is given by pairing of vectors and covectors. And the bracket is given by this formula. Vector, vector, covector, covector, lead derivative, and then this, and then I can add an extra term where H is an arbitrary closed 3.1m. So this is completely classified. In the small category like this. We can also say something about the transitive ones. This is a theorem again with the follow, which says that every transitive one is locally, globally things are more complicated, but if it's locally, we can say that this looks like Tm plus T star m plus G, where G is a Lie algebra. But by this I mean it's product bound with the algebra. Lie algebra is real product of the algebra. Lie algebra with invariant pairing. So they are completely. So locally every such thing is given by the algebra with invariant pairing. And then I will not write you the remaining formulas. You can imagine that they go somehow. In fact, I won't even need this. This is just to give you some sort of explicit example. So the theory that I will develop will be kind of general. It will not assume exactness. But yeah, it's probably good to see at least one example of this. Okay, so what else did I say? Okay, any questions?
Maybe. The pairing is essentially multi-general.
Sorry?
So the pairing is multi-general.
Yes. Yes. You're right. Yeah, I was a bit quick. It's non-degenerate, symmetric, invariant, bilinear, sorry, non-degenerate bilinear symmetric pairing.
So that's how you identify ELE stuff.
Yes. Yeah. This is crucial. That it has to be non-degenerate.
And a question locally means that your M is some neighborhood of a point.
Yes. Right. Yes.
Okay.
Yeah.
We write n times g or something like
Yes.
that.
Thank you. Yeah. Yeah. Okay, very good, perfect. So now another thing. So let me go to connections. Okay, very good. So definition. The Courant algebroid connection, or generalized connection, or e-connection, or just connection if you want, is the following map. So it's something that I will call D. So it's a map where it's like an analog of the ordinary connection, and you replace tangent one by E. That's kind of the whole philosophy here that you are. Although there is some link here, you really want to see this as some sort of new tangent one, some link. So you replace everything by E, and then you require. Again, you can write. You will. This will be the notation. Section, and if you put the function here, then you want that you can take it out. This is what we call connection. And for any U and V, and if you put the function here, then you want the property, the usual one, except you have to replace. You have to use the anchor map to get a vector field with which you can differentiate D. Now, if you look at this condition, which is the same kind of property as here, so you see that this D of U kind of looks very similar to this one. Of course, they are different because this expression is linear, like function linear in here, when this one is not. But at least like this object and this object have similar properties when they act on functions and sections of the Courant algebra. So what I mean is that out of this, you can just, in the same way, using line limits, you can extend this to act on any tensor power, section of the tensor power of E. Okay, so I will use this again. Just okay, so we have now a linear derivative and we have a connection, and just as before, we will now require change the definition.
We can just.
You mean like linearity or?
Yeah. So additivity for one component doesn't complete linearity because you have just multiplications.
Right, bilinear.
But I mean, this should imply bilinearity, shouldn't it? Yeah, because this thing tells you that if you bilinearity with respect to function to numbers, this tells you how you behave.
There is also additivity. You can one sometimes forgets that you should also tell that it's bilinear, like with respect to addition.
Good point. Thank you. Okay. So thank you. Okay. If I write it like this, it's better.
Yeah, I also always forget about saying that it's actually the additive or whatever.
Right. But this thing means okay. Yeah. It's like it's a linear map. Yeah. Okay.
Yeah, they say that it's linear.
Right. Yeah. Okay. So thank you. I remember they did this at many talks actually. Now that they say it, but yeah. Okay.
Yeah, I always forget.
Okay. Very good. Perfect. Okay. So yeah, and to finish the definition, I will also ask that the pairing is preserved by this D. Now, don't confuse this pairing with this metric on the manifold. So this pairing is a part of the Courant algebra, so it's a part of some. It should be thought of as like an analog of this space. So instead of having bare space, we have like some slightly more complicated thing, but we still treat it like a space. So we still don't have like the Riemannian structure of it. Okay, so we are still in this first slot. Okay, now for connection, we can define torsion. T is defined as T. It eats two things and starts as you would expect it to start. But then this is not a tensor in this context, so you need to correct it. It turns out that if you add this thing, then this is now a tensor, and moreover, it's not just a tensor, but in fact, this is a, it's not, it's like significantly linear in both slots. So it's a section of a bundle, and furthermore, it's a completely antisymmetric thing. I'm identifying E with E star. So, okay, so this is a torsion. This is a relatively well-established notion here. And okay, just to finish this preparatory part, let me just remark. So the other bit that I will need is this house density. So, okay, presumably, let me just briefly recall what this means. So does it mean to be a half density? So half density is just a formal way of, okay, formally defined. It's the vector bundle which is associated to the frame bundle via some nice one-dimensional representation of the group GLN. But if you know this, then you probably know what half density is. So just like the way to think about it is that it's just something that if you have this section of a bundle, okay, section of some very nice bundle, line bundle over M, it's a section sigma, and it has this, and this line bundle is very nice because, for instance, if you have if M is oriented, then the tensor power of this bundle itself is currently isomorphic with top forms. And but importantly, this makes sense for any manifold. Doesn't have to be oriented. Like all manifolds have well-defined line bundles of half densities. And in all cases, it's true that if you take two half densities and you multiply them, or if you take a square of the half density, then you get something that you can integrate. So you have a well-defined integration. Subsets. Right. And so if M is compact, then this thing gives you a nice Hilbert space. Okay, what do you think? So if you wish, think of it as a square root of the volume form or something, square root of the top form, but you can make it precise. And okay, and just as a notation, so half densities will be denoted like this: the space of half densities, so sections of that line bundle. Okay, sections of this L, I will call them H, where H stands either for half density or Hilbert. And actually, I will not use this. I will be only using invertible half density. So this is a everywhere non-zero half density. So this will be for the people who know this. This will play the role of the Valach in string theory. Okay, so this is the end of this formal preparatory part for the before we go into the Riemannian stuff. So please do ask any questions before I iterate this. So I should use this one, right? Okay. Some questions? I'm sure there are questions. I still have like 10 seconds. No?
So maybe I have a question. How to come up with the definition of torsion, for instance? Why do you define it this way?
Because the first three terms is how you define ordinary torsion.
Yeah, sure.
And
the last one is.
Okay, so pragmatic definition, pragmatic answer is that this is the thing that makes it into a tensor.
Okay.
Maybe I should Is it okay if I do this, or should I cover? It's okay. That's a sort of pragmatic definition. It doesn't explain why it's a good idea to take it. So, in fact, if you look into physics papers, and the way they justify it is that the physicists have a way to write down the thing that I just erased. I did write it on the exact Courant algebroids. They have some sort of formulas how they write it, and it uses, if you write it in coordinates, then so physicists have a way to write essentially Valach derivatives. So they know they have a formula here which kind of uses explicitly a choice of frame or coordinates. We use some partials, and then they say that you can do the same thing if you replace all the partials with a connection, and then they define torsion to be the difference between these two.
Okay.
And then it coincides with that definition. And this thing is funny because it also works in not just in this setup, very generally for other types of algebroids.
Sorry, the camera seems to have gone out of zoom, out of focus.
Yeah.
Camera out of focus?
Yes.
You have to wait.
Yes, sorry, this is for a screen. Yeah, hi, Fridrich.
Vigorously but slowly.
Maybe raising your knee somehow affect focus.
So
the camera started to be more alerted when.
Can we adjust it manually?
I don't know.
Maybe we can turn on
Maybe some magical words like focus. We so tried. Yeah.
Is it better?
It's getting better without you, but yeah, it's focused already.
Just write on the blackboard. We have big blackboard.
Okay.
Is it better?
I guess so.
Okay. Perfect. Okay, so now let's do Riemannian geometry or generalization there. So generalize Riemannian geometry. Okay, this is maybe not very visible, but I will generalize Riemannian geometry. Okay, so basic object, metric. So there is many ways. Now why haven't they used that? Okay. Let me continue there. I forgot that this is please. Okay, sorry. So definition. This is part 3. Definition. So a generalized metric. So there is many ways to say what this is, and they all are fine, and sometimes even equivalent. But it's like this is an example of a sort of negotiable definition. So depending on what you want to do, you can make it less or more strict. So at the very least, the thing you require, I will say, so it's an endomorphism, vector value endomorphism. So something that maps fibers to themselves. Endomorphism, curly G, that goes from E to E, such that idempotent square to 1 symmetric. So this symmetric transposition uses the invariant, the pairing on the Courant algebroid that we have. So this is the very least I think that you want from generalized metric. So if you have such a thing, since it squares to 1 and all that, then you can actually, this gives you a decomposition of E into as a vector bundle into 2 sub-bundles, where V plus minus are plus minus 1 eigenbundles. Okay, and now I will put some extra conditions. Okay, so let me enumerate some other conditions that I will require for today. So if you look into the paper, then we do things more generally, but for the presentation I found it the best to just restrict a little bit, so that I don't need to write all the assumptions all the time. Okay, so let me assume first of all that M is compact. Okay, this has nothing to do with generalized metrics. It's It makes it nice. Then G is positive definite. Okay, so it's an endomorphism, but there is a then the pairing, so it makes sense to talk about positive definiteness. Slightly more critical one. If I take anchor and I restrict it to B plus, where I get a map from B plus to C, I want this to be an isomorphism. So this is true in all the interesting examples that people study. And the last one, which is totally critical, unless you know what it says, is that rank of B plus of the bundle is different from 1, and the rank of B minus is different from 1. So this last sort of strange looking condition, again, let me say that in all the interesting examples, this is satisfied. It needs to be there so that the proposition, the theorem I will write next is true. You might not, you can probably achieve all the theory without that theorem, but it makes it much more cumbersome. So I would assume this to make our life simpler. Okay. Now, with all of that, I can make one final definition. So now that we define the torsion, so we say the P is Levi-Civita. It preserves the Hilbert metric, the Levi-Civita for this metric, and its torsion is 0. Okay.
Excuse me, I missed what you mean by positivity of G. It is positive in respect to this pairing?
Yes. Yes.
Do you assume something about its pairing?
I was very brief at the beginning. You only assume that it's symmetric, non-degenerate, bilinear. It can have a typically has not is not positive definite. Usually has a split signature or.
Okay.
Right. So in fact, that's maybe a good point here that this condition should be this condition 2 should be equivalent to saying that this Courant pairing, if you restrict it to B plus or B minus, then it's positive and negative definite respectively. Positive definite. This thing acts as an identity of this guy. So yeah, I think that should be true.
The B plus is then the biggest.
Yes. Yes. The biggest positive definite subspace. Yes. Yeah, thanks. Okay, so now a theorem. As far as I know, this is first full generated proven by Mario Garcia Fernandez. So this says that so for any generalized metric and for any invertible Hall density, there exists a Levi-Civita connection Z such that which further it's not just Levi-Civita, but it also satisfies a thing, the common property that if you take its associated divergence, so if you take trace, you take D of U or some section U, and you get so this thing is now this is now a section of E star tensor E, so you can take a trace. So this is how the way I usually construct the divergence of connection, you take a trace. And I want this to be aligned with respect to the divergence given by the density of density. So, okay. So if this is a Hall density, then it's square the density, and by this I just mean that you take the anchor, turn your section into a vector field, and then calculate the divergence in the usual way to take the leader derivative. So this is the ordinary derivative. With respect to identity. So okay, so what this thing tells you that Levi-Civitas are not unique, and you can specify some more stuff from them. So you not only require that they are compatible in G, but you can also require that their trace is aligned with divergence with respect to sigma.
So by Levi-Civita respect to G.
Yes. Yeah, I was a bit fast here, but yeah.
I'm a bit confused with the conditions and the definition. So for this, there's certain numbers here we don't want and the compound G to be positive definite. You know, these extra conditions that you mentioned not at all. So for generalized metric, we just have an endomorphism to define these basic conditions, and for that you have this there's certain numbers here. So this extra part is not necessary.
No, exactly. Well, actually, the only thing that's extra necessary is this unfortunate fourth thing. The others are, yes, the others are. The reason I'm having the other one is later for this elliptic theory and stuff like that.
When you choose the right one.
Right. Yeah. Yeah. So this is a very general. Yeah. The only thing is unfortunately it requires this because there's not enough freedom for if that is there. Okay. Perfect. Okay. So let me call. Unfortunately, this still doesn't fix the connection. So let me call notation. All the Levy-Theta connections let me call a set of those by LC of G and sigma. So these are the ones that satisfy these properties. It's Levy-Theta with respect to G. With respect to G. And it satisfies this thing. So let me call the set of those like this. And let me also call the space of generalized metrics by M. So M is the space of generalized metrics on our given Courant algebroid. So for all of this, well, I didn't say it. I meant that we have some fixed Courant algebroid. Okay. Now, one final notational remark before introducing tensors and stuff. Okay, so notation. So I will use E alpha for frame E. And when I have a generalized metric and I have this splitting of E into this P plus and P minus, I will call the respective frames with Latin letters and Latin letters with some ornamental dots. So this thing is a frame of B plus, and this thing is a frame of B minus. And the reason I'm introducing this is that I will use this notation for the connections, which some of you are maybe familiar with. So I introduce the connection, and obviously, if I write like that, then I want the connection to specify two sections, U and V, right, to make it work. But there is in fact there is this other notation that's sometimes useful, and in this case, it's extremely useful. And that is kind of what many physicists use. So if you take, let's say, some frame E alpha, and you have some tensor, let's say you have a tensor. Let me show you an example. So you have a tensor, you have a section of this kind. Then whenever you write something like d alpha, d beta, so you don't fill in sections, but you fill in indices. I apologize if this is too trivial. It's good to stress this out. So this thing is by definition the following thing. I take T, I take D of it. So T was a section of this guy, but if I act with the covariant derivative, I add another index for the thing that I differentiate. So this is a section of E, and then I take the exterior the covariant derivative of that, and I get a new tensor, and then I take the alpha, beta, gamma, delta components of that. Okay, so this might look like a formality, but in fact, if you want to write it in terms of expressions like this, then the same expression you would need to write this T, and then gamma delta, and I think minus T gamma delta. So the energy of this notation is that whenever you write things like this, and these are manifested tensor or quantity. So these are components of a tensor. Well, if you use this notation, which is useful for other purposes, but in this case, it's kind of not clear. Like this thing by itself is not tensorial in this indices. So this is a very convenient notation, and you can develop the same calculus that you have, like it satisfies like this and all that. And this allows you to write things much quicker, especially when there's lots of indices. Okay, so and okay, One more thing I wanted to say, because as you noted, maybe so far there was no proof. So let me show you a proof of the following proposition. So suppose that I have a Levi-Civita connection for some g and sigma, and I define the Laplace operator to be g alpha beta d alpha d beta, and this can act on any tensor powers. Let's say this acts on k tensor powers, for instance. So the claim is that this is elliptic. Now okay. What is the proof of that? It looks very suggestively written that it should be elliptic, but let's check that. So the first step, take something else. Take this thing. We don't contract. I didn't say this, but whenever I'm raising and lowering indices, I always use this pairing for lowering, raising indices. Okay, so I use that thing to write down this expression, and now I add on a function. Okay, so f is a function on the base. Now look at this. So if you look at this guy in here, so how does the covariant derivative act on a function? So it's just a function, so that it just acts by the anchor map, so in the same way as the bracket. And if you think about it, then this is actually the same thing as having this curly d operator acting on it. So this curly d, that this was just shorthand for differential, and then the transpose of the anchor. So okay, you can just replace this thing by this guy. Now if you look at it, and using that convention, what they're taking is that you have d of some section. This is the section. You take the d of it, and then you take the trace of it. Okay, this is what alpha means. And by the definition of what it means to be Civita, you know that what that thing is. So this is sigma minus 2, the derivative is the rho of df of sigma squared. But now, this d contains the transpose of the anchor, and that composite anchor reaches 0. So this is a interesting fact of life that actually this kind of first attempt for a Laplace operator is actually, well, not very good. It's trivial on functions. For me, this was slightly puzzling when I saw it first.
That's impossible to
Yeah, probably it will that, yeah. Yeah, so things like this happen, that you have like something that looks like a second order operator, but in fact all the second order derivatives, the second derivative, they just cancel each other. And this is one of the cases. Okay, so this was just on the functions. How does that the operator act on functions? Now imagine that I am acting on some tensors, some sections of E with itself. Okay, so so what happens if I now act on some general section? Okay, for product. Okay, so imagine that you work in coordinates of frame or something. Then a section of this is some coefficient functions, and then some frame, tensor frame, etc. And when you're acting with an operator like this, you can either hit the coefficient function or you can hit the frame. But hitting the frame will produce some Christoffel symbol, so it will not increase the derivative. So the only way you get the highest term in terms of derivatives for this guy is when you act on the coefficient function, and that simply coincides with this one. So what this thing says is that there is in fact no higher order, like that there is no second order term in this. This is the first order differential operator. Right. Okay, and that's almost the end of it, because now if I go to actually what we want to do, the Laplace. Okay, but we remove the indices so that it looks more like an endomorphism. So this alpha it runs over all of E, but if you split it into B plus and B minus, then you remember that this thing is the identity of B plus and minus identity of B minus. So what it means in terms of indices is that you get this thing minus dA dA. Okay, so you split this alpha into A and A dot, and if it's A and B, then this is Kronecker symbol, otherwise it's minus. So it gives you this thing. But now if you write this guy again as B alpha, D alpha minus dA dA, and what you get is that this is 2 dA dA minus D alpha, and we know that the second thing is actually first order. It's in the second order, and this thing, by the assumptions that you maybe don't remember, is actually mostly definite. So for this one, it's easy to see because we know one of those conditions that I assumed about was that rho restricted to B plus is an isomorphism. And also we saw that the metric restricted to B plus is positively definite. And these two conditions tell you that this is actually positively definite. The symbol of this is it's positively definite, and this thing is just first order, so it doesn't matter. So this is okay. How much time there is still? We started a bit later.
Yeah, that's true. So about 15 to 20 minutes.
Okay. Yeah, this is very. Okay, so at least one sign to check that we have a Laplace operator and the listing that works. Okay, and now I can go to the promised curvature tenders, which I guess some of you are looking forward. So suppose that I take D to be any connection, and I will require torsion freeness. So it's torsion epsilon. Then I can define the Riemann tensor, Rm, of that connection to be the following thing. So I take 4 sections, W, Z, X, and Y. And okay, this is the most painful part. So before I finish writing, let me say that this is the one that coincides with the one in the paper of Brano and Honda. And with all the stuff that people do in our fluid theory, all the way going to Siegel. Okay, so the first term is what you would have in ordinary geometry, that would be it. And here you get unfortunately a couple more. Okay, that's it. Okay, so don't try to remember it. It's just something. Now proposition. It's a little bit of gymnastics. Is that this is in fact a tensor. It's a section of the 4th power of E. Remember that I'm identifying E and E star. Furthermore, it has all the usual symmetries. So it's anti-symmetric if you swap these two guys. It's anti-symmetric if you swap these guys. It's symmetric if you take the first pair and second pair and swap them. And then it also satisfies the algebraic variant. So the algebraic variant is hard to prove, so we don't do that, but you can find it in the paper of Renier Honda, for instance. And yeah, so it has the usual properties, symmetric properties. And the question about the question of the Bianchi identity is more subtle here, like the differential one. Okay, that's the end of Riemann tensor. Now to go to Ricci, which is the thing that we are interested in ultimately because we want to study Ricci flow. So suppose now that you have a Levi-Civita connection, okay, so not just torsion free but Levi-Civita, and then I define 2 tensors. I will call them Ricci bar and Ricci, These are both endomorphisms. So again, vector bound maps from E to E, and I define them as follows. If I define them as follows, so Ricci bar is the thing that you would expect normally. So this is the one if you contract the Riemann generalized metric. Oh, stop something. Yeah, I should have. Okay, there we go. No, sorry, no, sorry. This is just this is Ricci. Sorry. There is no metric here so far. Yeah, just compare the Riemann temporary. Okay, but this turns out to be not such a great object. So we define another one, which is this Ricci, and the quickest way to write it is as this particular combination of endomorphisms. Everything here is endomorphisms, so you can combine them and you can add this extra multiplication by G. Now, why am I doing that? Okay, so proposition. These guys are both tensors. That's kind of clear from the fact that Riemann was tensors. But also they are symmetric. That's actually also extremely simple to see from the symmetries of Riemann. But okay, how does it look in terms of indices using that decomposition? So if I take Ricci of A, B, or Ricci of A dot B dot, then this is 0. And in the mixed component, when I have A, B dot, this is 2 times Ricci bar A, B dot. Okay, so what this thing tells you is that this Ricci is just a projection of it's essentially the same as Ricci bar, except you set some components to 0 and multiply it by 2 for whatever reason. And the reason I'm doing this is that Ricci, in fact, is independent of D, and it only depends on G and sigma. And not only that, but the dependence on sigma is very mild. So I take Ricci, we call it G and sigma, and I multiply sigma, the half density, by exponential of some function, and then I compare it with the previous Ricci. And this thing is just a Lie derivative with respect to this of the metric. So, yeah, that. Okay. There is stuff. Yeah, any questions? Is there water somewhere? Oh, there.
Just a clarification question. Maybe there is some miswritten definition of a Ricci bar. I mean, probably contraction of Riemann, right?
Yes, that was RM. Yeah, this is very badly written.
Okay, I get it.
Thank you. Yes. Again, any other questions?
Is there any notion of Fourier transport and monody in the channel?
Good question. As far as I remember, I think it's more subtle here. Maybe hold on.
Not yet.
Yeah, some people working on more.
Yeah, I mean, what makes it slightly subtle is that you are differentiating with respect to a section, and that section usually has like a tangent bit, like in that example, it was tangent plus cotangent, so it's like it has more stuff in it. So it has stuff in it which doesn't correspond to directions on the base. So you can differentiate with respect to not vector field, but something more general, and that makes it more subtle. But I mean, I'm pretty sure that there is a meaningful motion if it's reformulated in some convenient way. But I don't know. Okay, so the last one that remains is a scalar curvature. So again, take B to be any Ricci beta. And then we just define scalar curvature in the usual way as a contraction using the metric of Ricci bar in this case. Because the contraction of Ricci will be 0. Okay. Again, proposition. R only depends just with Ricci on the G and sigma. And maybe an interesting observation, you have some sort of Bianchi identity for this one. So you have this contracted Bianchi identity. The reason you have this one is that there is some sort of variational principle that you can use it to derive from. Yeah, that's a useful thing sometimes. Okay, so far, some of you have seen the versions of the story before. Now, in some sense, it's just a reformulation up to now. So maybe some propositions which are, if not new, at least less famous. This for me. So suppose that you have a family of generalized metrics depending on some parameter S and some family of sigmas, and you have a Ricci beta for time 0. Ricci beta for G0 and sigma 0. Now, this will be a very vaguely stated proposition, but okay, let me. Then there exists a canonical. So as you've seen before, there is usually many Ricci beta connections, and there is typically not a canonical one. But it turns out if you do a variational problem, then there is a canonical variation if you start with something. There's a canonical family dt, that's Ricci beta for gt and sigma t. And it's even better, you can write down this explicit formula for it. Or at least, well, there is an explicit ODE for d dot. For the there is a d dot is something very explicit. You can write right hand side explicitly, and I'm not doing that with variable, but in principle, yes.
It satisfies that d at 0 is d0.
Yes. Thank you. I mean that there is an explicit formula for it. Yeah, I'm sorry. Here I wanted to skip some details. So, yeah. Okay. And now the last proposition before finishing is that okay. Suppose now that you have some G of S and sigma of S, some families just right there, and suppose also that you pick some family of Ricci betas. It can be the one from here, but it doesn't have to be just any Ricci beta, any family associated with Ricci betas. Then, if you now take the curvature tensors and you differentiate them with respect to S, if you take partial S of Ricci, let me just write Ricci dot like dots. Ricci dot is okay. Let me set chi to be G dot, and let me set tau to be sigma dot over sigma. So this is a function, and this is some tensor. Okay, then the explicit formula says that this is in fact -1/2 of the Laplace of chi minus 1/2. You are just using a chain rule to you have a formula for these things, and it's just a very, very horrible chain rule, so you can in principle do it. but it's very powerful. G plus lower order terms, which are lower order in terms of differential operators acting on chi and tau. So this is the second order operator, and this, if you look at it in terms of tau and chi, second order operator again. And unfortunately, this is quite horrible, but you can write it explicitly. And then there is a scalar curvature, which is simpler, and that one says this. Alpha beta I gamma delta minus 4 times Laplace tau plus lower. Now the great thing is that we showed before that Laplace is actually elliptic. So, okay, just regard this as a technical lemma. Now just close. So I still have like 5 minutes. Okay. Any questions? Now we come to grand finale with the most exciting bit.
Sorry, why is it so great or talking that let me finish this. This Laplace is elliptic.
That's what is okay. Yeah, that's what it will come in the bits that I'm going to say now. And then that comes in the theory of elliptic differential equations or whatever. So it's known by some big theorems that if you have some horrible PDEs, they can even be nonlinear, such as the one that I'm going to write now. And as long as if you calculate the linearization and if you get that the term is the thing you have here is elliptic, then you can conclude that the equation that you have admits unique solutions for some short time. So it required for the elliptic theory.
But it's not really elliptic PDE, right?
No, it's not, because it has these other terms. Yes, exactly. That's what makes yes, but yes. Yeah, I will comment on that. But the important point is that this other term, which makes it non-elliptic, that one has the form of a Lie derivative of the metric with respect to something. That's kind of crucial. I will comment on that. But let me just announce the end. So, generalized Ricci flow. This again comes from physics. So, first thing to notice is that this space of fields that we have, which space of generalized metrics, times this sigmas, the space of invertible half densities. So this thing has a natural metric. There's a nice metric. I mean, it's interdimensional, but at least I can, in a sense. So suppose that I have two vectors that are tangent to this one. So elements in here are G, and this is G, this is sigma, and I have a vector here. So vector, you can imagine that you have a family of G's and a differentiate. So this would be a vector, another vector, and let's say I compute their scalar products at the point G sigma in here. Okay, so I want to give you a formula, and the only thing you can cook out of this data is you take this G dot, and you take this thing and multiply by sigma squared, so you get density and integrate. So this thing means that I take the inner product induced by G. Okay, so yeah, I take this thing as your inner product, which we know is positive. That means that's how we see it. Okay, so there is only one expression that you can write. You can put some constants. We put 1/8. If you have two vectors that are tangent to this one, so some variations of this half density, then again, there is only one thing that we can really write. Maybe after this -2, and that's sigma dot squared. And we want that if you take the cross thing, that these are 0. So these are orthogonal to each other. Okay. And then I can define Einstein-Hilbert functional. As a function on this space, metric, half density, and you just take the scalar curvature. which depends on g and sigma, and then multiplied by sigma squared. And this coincides with the string effective action. And now I define generalized Ricci flow is the flow of minus half gradient of S. S being a function. I mean, this is infinite dimensional, but I mean, I can write it. I can take this as a heuristic thing, but I can write this explicitly what it means if I just plug this formula, this variation using this into this, then explicitly this means that G dot is minus 2 Ricci and sigma dot, so the thing that I had at the beginning. And okay, theorem, short time existence and uniqueness. Okay, so now just a comment on how this is proven. Then maybe I can say 2 sentences. And okay, so how this is proven. So so this equation. So first of all, forget about this equation. Okay, this will be a sketch anyway. So let's just focus on this one. Let's ignore the fact that there is some sigma. So if this would be the only equation that we would have, then the problem with that equation is that. So the calculation that I'm doing here is essentially I'm linearizing this Ricci in terms of generalized metric and sigma. Okay, so this is essentially what's happening here. I linearized it, and I got some expression like this. Now, this big theorem says that if what you have on the right hand side is elliptic, so if this would be all, and if this term were not there, then I could automatically conclude that there exists a unique existence for some short time at least. Unfortunately, there is another term. But then you can do this thing which is called the third method, which is done in the ordinary case. And what you do is that you realize, aha, this thing looks like derivative of g with respect to some section. So now suppose that I have a solution to my equation, this equation. Having such a solution, I can write what this thing is. It's some family of sections, depending on time. Now I can integrate those sections. Sections induce infinitesimal automorphisms, just as sections of tangent bundle induce automorphisms, my solution to the Ricci equation, then the resulting thing will satisfy the same equation only with this term. Okay, so there is a trick. I know that I'm perhaps 300% faster than I should be, but yeah, so there is a standard method how to deal with such things. You can kind of remove this term by pulling back by a family of automorphisms which are generated by these sections. Unfortunately, this allows you to go one way. To go the other way, you can still do it, but you need to determine these sections, and for that you need to solve a PDE again. And that's where the new problems arise, because that new PDE is almost elliptic, but not quite, and then you have to play with it, and you have to use some slightly subtle things, but ultimately you can make it work. So that was the shortest proof of this thing.
Short time.
Short, exactly. Okay, and then just to okay, maybe.
Yeah.
Or should I finish already? I mean, I can cut it.
2 minutes.
Okay.
No problem.
Okay, so I just wanted to write two further theorems which are maybe of use to some interested people, since we came on this painful way. So along the flow, this Ricci flow, we have the following interesting identity that when you take derivative of r, the time derivative of r, then this equals this plus Ricci, where with respect to this positive definite thing. So this is a very useful identity. So this is along the flow, because it tells you, in particular, a corollary, you can show that using some standard arguments. It implies that the infimum of the Ricci of the scalar curvature is non-decreasing along the flow. This is called simply scalar curvature monotonicity property, and it's very important apparently in this Ricci flow Oops. And second, last thing, if I now define a so-called lambda function now, if I remember correctly, this one from Perelman. So you take your Einstein number and you find the infimum over all the sigmas of unit weight, such that the square is 1, the integral of the square is 1. So then the theorem says, this is slightly harder to prove, so pick some T1 and T2, T2 larger, then along the flow, lambda T2 is bigger or equal to lambda T1, okay, so similar to that, but also the equality here only happens if and only if the solution is a solid zone, which means that it's some sort of solution that it's like a fixed point of the flow. It's going to be more general fixed point. It's like a fixed point of the flow where which can evolve, but only evolves by automorphisms. So, right, this is harder to prove. It's usually something that we derive that's called steady harmonic estimate. But yeah, so all of this is derived there. Yeah. At the very least, I hope these formulas might be useful to people for various purposes, hopefully. So, well, thank you. Sorry for going a little bit over time.
Thank you very much for your nice talk. Now let me open the discussion panel. So, if you have any questions?
Yeah, so two pointy question pointing to the future. So somehow do you have like a certain understanding of potential singularities for the solutions of Ricci flow? And hence, you know, like thinking about Ricci flow, you always think about the works of Yao, you know, like identifying this singularities with the potential geometries like predicted by the generalization conjecture of Thurston. So, like, do you have at least like maybe like a dream feeling of like whether something like that in some particular situation?
Thank you. That's a very good question. I don't, unfortunately. I come so far. I come more from this kind of stringy Ricci general geometry perspective. So far I've been exclusively focusing on like getting this done, and the next thing I want to do is to understand how these things work in the classical case and try to generalize it. So this, like we very much hope to be able to extend at least some of this of the behavior and the singularities and all of that. But this was like step number 1 or 0 toward that. So we plan to do that, but so far I don't have anything interesting to say about it, except that I believe that everything should work. In some sense, it's like a crazy thing about this is that it's somehow, in some senses, this is nice. It's more complicated, but in some very particular aspects, it behaves nicer than the original. For instance, the equations of motion that you are getting from here is literally you are getting the Ricci flow. While in the ordinary case, when you only have the metric, then you get the variation of this doesn't give you the Ricci tensor, it gives you the Riemann, and then it gives you the Einstein tensor. And here it kind of string theory kind of nicely takes care of stuff. It offers some very useful formulas, and in particular, you get this kind of very nice evolution equation. So yeah, but presumably it will be harder than the classical case.
Okay.
So for fixed generalization to sigma, what kind of structure does the set of Ricci?
Oh, it's an affine space modeled over sections of some of a particular bundle that you can write it explicitly that like if you take two yeah, I mean it's if you have two such things, then they differ by something that is a section of E, tensor E, and it's some particular representation of the orthogonal grouping here. So there is like if you decompose this into all the OP, Q representations, there's like a lot of stuff, and some part of it will correspond to a subbundle, and which is the one over which the set is modeled.
Because the condition is the kind of trace of the U equals to the value of this or something that's.
Yes.
Well, it's not close under addition of D, right? But if instead of sigma you consider like sigma as a scalar factor, then it's fine, right?
Right, but like that condition you saw, at least that made it affine, because if you take two of these and you multiply two connections and you subtract them, then the right hand side vanishes if it's the same. If they both correspond to the same sigma, then that just cancels. So that's why it's affine.
So in this proposition, if you check some kind of
Again?
in this proposition, you check some kind of static equations where if G, S, and sigma S are constants, can we still get some non-trivial curve in this space? It's hard to say because we don't know what's on the right hand side of this equation. D dot equals something.
This one.
Yeah. So if you have some kind of static background, and it's a constant generalized metric and constant section sigma, so do you can you get some kind of non-trivial solution for this DT?
Meaning for this one. So this thing, whatever it is, it's a linear function of G dot and this tau dot, I think. So the tau was the sigma dot essentially.
Okay.
So if that was yeah, just you take those things and then you do some horrible things with them, but linear, and you get the d dot. I don't know if it maybe doesn't answer your question.
Well, I mean, simply speaking, if G of S and sigma S are constants, is the right hand side zero?
Yes, because this is linear in those things. So if you fix them, if the class is just finite, then this is zero and this is zero. So this, no, this is a, no, you don't get anything interesting that way.
One question from online audience, so Jungro.
Hi, am I audible?
Yeah.
Hi, yes. So, well, yesterday, Carlo Shabazi gave a talk here where among others, he, talked about your work in very favorable terms. But also, I mean, I learned what solitons were. And one of the things he mentioned was that in the ordinary, as a non-double case, the solitons are such that when the vector field involved, when the diffeomorphism involved is a gradient flow, then the solitons then correspond to when the vector field is a gradient flow form, then the potential for that gradient flow is supposed to be dilitons stuff. So what's is there an analogous story for the interpretation of solitons in the generalized geometry, in the general complex geometry case?
Sorry, I missed the last sentence before that. So what happens in the classical case?
Well, so in this setup, has the dilaton entered in the sense that the general metric encodes on B and G, but not the dilaton, right?
Yes, that's right.
And I understand that in the ordinary Ricci flow case, the solitons are generalization of the class of solutions to Einstein-Hilbert, as in the generalization of the class of Ricci flat metrics, and the generalization is that I can allow for diffeomorphism.
Yes.
Such as the point up to diffeomorphisms, and that when the diffeomorphism is the flow is a gradient vector field of a scalar field, then the scalar field in question can be interpreted as a dilaton in the ordinary case. As the question is, I mean, what's the physical interpretation of the solitons here? In the Ricci flow case, it was supposed to have something to do with dilatons and cosmological constants, if you happen to have it. Here, what do the solitons mean physically?
Good question. Sorry, let me recall. So the way we do it is that I think for us the definition of a soliton is it's a property of a generalized metric. So we don't put a dilaton there. So it's like we say G is a soliton. I think this was the condition that G is a soliton. Such that there exists a sigma. I think it should be something like this. Such that there exists a sigma for which Ricci G and sigma is zero. And here the important thing to remember was that if you change sigma, then the stuff changes by diffeomorphism. So there was some early derivative of generalized metric with respect to something. So the fact that with Ricci, okay, so this thing kind of means that the origin of G for any random sigma, this thing will be some definitely derivative of the metric. Okay, I want to. I don't remember from the top of my head, but we do comment on that in the paper, so you can have a look. Sorry, I don't remember it from the top of my head.
Okay, I will. Thanks.
Thank you.
And there is another question, probably.
Yes. Hello.
Yeah.
So, I guess this might be a question which has already been asked in some other contexts, but then so there's this thing in the world of curvature in generalized geometry. There are like different notions people have tried out, right?
Mm-hmm. Yes.
And the one you now introduced is one of them. And then I was wondering, because there's this work by Mario Garcia Fernandez, right? And he has this slightly different notion of curvature, using like the generalized metric in a say more explicit way. And he has also developed like theory of generalized Ricci flow, and I think he has even worked with Jeffrey Streets as well on this generalized Ricci flow. And I was wondering, like is like the relationship between these two concepts, because of course the curvatures, they're related somehow. The one you introduced is like has more terms, and the one that Mario uses is like half the terms or something like that. And but has the relationship between the two curvatures and the two Ricci flows generated by these two different curvatures, like, is it clear what the relationship is?
Yes. So in the case when there is a half density, yes. So in the case of half densities, those things should be the same, or they should carry the same amount of information. So the one that Mario uses typically, that the Ricci tensor is anti-symmetric, but it's also but in both cases, if it's symmetric or anti-symmetric, it still only has how to say like it carries the same information if there is a half density. If there is more general divergence, which I skipped over today, but like you can do it for divergences, then it also coincides if some conditions for the divergence are satisfied, namely some compatibility. So in the usual interesting cases, those things are completely the same.
Okay. Yeah, because like at least like my problem, let's say like Mario's curvature seems it's like a direct generalization of, like, it's the naive thing one would do, right?
Yes.
Whereas the curvature that you used, like somehow it somehow also seems natural in the sense that you want to force the classical symmetries of the Riemann curvature. And but then if they do give the same, if they have like the same information, yeah, okay.
So if I remember correctly, then what Mario does, I might misremember, but I think he only assumes that the inputs are. I think the inputs are, some of them are in V plus and some of them are in V minus.
Exactly.
I think the formula that I wrote introduced is directed to that one that Mario has. If you have those, this one is like for general sections.
Yeah. Okay, no, but that was just my question. So if they do give the same thing,
yes,
at least in this half densities case, yeah.
Yes.
Okay, thanks.
Thank you.
Okay, so any other question?
I guess the classical correction flow can be used to prove geometric inequalities, right? Like the isoparametric inequality. I guess those smoothing properties you were mentioning at the very beginning.
Yeah, I don't know about that in this context. Sorry.
So my question would be like, there's some like geometric meaning in this direction, like whether you can use those equations, those flows
I suppose
to prove some geometric inequalities.
I suppose so, but I don't really know. We haven't looked into that yet.
Okay, so there's no other question. Let me thank the speaker again.